So the next lecture is related to memory management. And up to now, we have seen how to profile the most time consuming functions, right? And that could be related to memory allocation, memory duplication, and also to the number of computation that we are doing in the code. This part will be related to the memory management. So this is the function that we used before. At here, on purpose, I am defining a large list to see the details of the memory in more uh, with more detail. So this is how our proof work, and this can be also used for profiling the memory. But here you need to add this memory profiling flag equal to true. And you close the profiling analysis as we did before, and then close the code that you want to profile in between. So this is familiar to us now, and we get, besides the timing columns that we saw before, we also get the memory that was used during this calculation. So notice that these numbers are quite big. These are in megabytes, and uh, but this doesn't reflect the whole memory that is being used by the code. It's just that it is an upper bound, and the memory released is not considered for this profiler. But anyway, I like to use this data as an upper bound for the total memory that is being used. Because sometimes when on the fly, there are some peaks in memory consumption. So, and this could be a problem in your code if you don't consider the peaks and only the final memory that is being used. So a more detailed way to explore the memory is by using the garbage collector, which is given by the GC function in R. So if you want to get reports on the fly, you can set the flags GC info. And here, for instance, I start the baseline of the simulation of the setup, and I call here the garbage collector at the beginning, and I get a report. So during the process, if I want to get some reports on the fly, I set the GC info function to true, and then I start some code analysis. So here I call the siml function, which was the pi calculation function with the added large list in between. So something that you will observe here is that R is doing some memory allocation and also memory release during the simulation. So this is something that you don't see in general, just when you call these flags. And when you are done with the profiling analysis or monitoring the information on the fly, you set GC info equal to false. So also at the end of your calculation, you can also call the GC info and get a new value for the memory report. In this way, you can see how the memory increased with respect to the beginning of the simulation. So, but take the garbage collector just as a possible value for the memory because R doesn't release the memory when you call the garbage collector, as many people think. R does it in a heuristic manner. It's just when the objects are not used any longer. So R tries to release them, but not when you call the garbage collector. So you can take then differences between the reports here given here for the vectors and also for the list, and get a value for that memory consumed. So this is what we will observe when we analyze the memory change upon creating objects. Initially, I reset the garbage collector by using this flag to have a baseline and to avoid any previous data that the garbage collector could have been stored. And then I get the values here for the baseline. And after that, I create a long list. And finally, I call the garbage collector. So here I get some differences in the values for the n cells, which reflects the list, and also for the vectors, which is reflected in this line here. So you can have a total memory that has been spent in this calculation. So the garbage collector can also help you if you delete objects, and then you can see how the memory is released. So, but instead of using the garbage collector at two different points and get the differences, you can use other packages like PRIR, for example, that provides you with some functions that allows you to study the changes in memory of objects and also uh, upon memory allocation. Install this package in a usual way and load that. And there is a function called uh, object size, which allows you to monitor the size of the objects. So this is one interesting plot, and you can see that R doesn't manage the memory in the way we expect. For instance, if you are growing an object, as I'm doing here, I'm growing a sequence of numbers, a vector, you may think that R allocates the memory gradually upon creating or adding an element to an array. R allocates a bit of memory, but that's a very expensive operation that R tries to avoid, and because of that, R allocates chunks of memory. And only when these chunks of memory are exhausted, then R tries to allocate the next chunk. And in this case, you can see that first R starts with some initial memory, then is exhausted, and R allocates the next piece of memory, and so on. Then it reaches a plateau when R considers that very short vectors are not needed and it needs to allocate a larger amount of memory. And then it repeats the same procedure. So the object size allows you to see how the memory changes or what is the memory spent in some element. Here, for instance, for this vector x, the size is 4 megabytes. That's what is reported in R. So, but look at this other example where y is a list of 3 elements that consists of x vectors. If we take a look at the size of this object, R will report only 4 megabytes. And that's nothing what we expected, because there are three vectors of size 4 megabytes. There should be 12 megabytes. So, but R tries to optimize the memory, and instead of creating a new object Y with three X elements, R creates a pointer to the memory address of X. And that's why you only see the value for X in this case. So unless you touch a Y, you won't see any change in the memory size of Y. You need to touch that. And you can do that either by manually by changing the value of the elements of Y, or by using some functions as we saw in the in the last exercise before, with n columns function that touches the vector somehow. So if we take the value, the size of these two objects together, we still see that is 4 megabytes. But what happens if we touch the elements, and in particular, we touch the first element of Y, and we change that uh, by zero, essentially by zero, because here I'm just adding and subtracting zero. So it's essentially the same element, but in this case, R will report 8 megabytes. I have modified the first element. I'm still pointing to the X element, but the last element is not modified, the other two. So that's why I only see 8. I would need to touch the three elements of Y in order to see the 12 megabytes here. So you see, R tries to help you by optimizing many things, but in doing so, it could create a bottleneck in memory because it does duplications for you. So this is another function from Prayer, which is called Mem Change, and it allows you to see the changes upon creating an element as well. So here I'm defining a function, and here inside the function I'm creating an object A. And if you monitor the change of the memory upon using this function, you will see that it's just about 1 kilobyte. This is nothing, right? It's just like zero. This value will depend on your operating system, and in general, this is a very small value. You won't see anything because this operation is done in the environment of the function. But what happens if we create the object in the global environment outside the function? Then you will see the real size of the object, which is about 200 megabytes. So another way to monitor the memory is by using the LineProf package. You need to install it, and uh, it's tricky. It's tricky to install that in some version of R. We have seen that in the first hour for the setup and installation procedures. But it also provides you extra information that is not available in the other functions that we have seen now. So again, this is the siml function, which includes a long list inside, which is put there just for purpose of analysis. And this function works by giving the argument uh, to lineprof as the function that you want to profile, in this case symlink, with some inner arguments. So the profiling of this lineprof function gives you more information. It gives you the allocated memory the release memory and also the duplications. So notice that here we didn't expect to have so many duplications because we are not doing that explicitly, but R is doing that underground. And that's why R most of the time is very slow. So this is one tool that you can use, and I succeeded installing it with R on Kebnekaise. And if you cannot do that on your machine, then we can do this setup on Kebnekaise later on. So some common issue, some common problem in R is that it loads all the data in RAM memory. So this is not a problem if your file is small, less than what you have on your RAM memory. So, but in general, this is a problem if you have big data. So there are several ways to do that in R, and one of them is by using the memory package. This package works by creating a backend file, and this works like a file handler, like a pointer to the file. It's not the real file. So install it in this way, load the package, and then with this instructor here, you will initialize a big matrix of this size, 10 to the 8 times 3. And this will be the name of the backing file. This will be the large file, and this file will be written on your directory. So please notice that in general, this size for the matrix can be quite big, like 10, I don't know, 10, 20, 30 gigabytes. But I don't use that for this exercise and for this example because it can fill out your disk easily. So be careful about that. And if you use that, it will generate a file of about 1 gigabyte size. So this is still uh, uh, useful for the purposes of doing exercises here. But you can use that for a larger file. So once you create the backing file, you can later on, another day, maybe next month, attach that existing file to another file handler and then use this file handler to work with. So one interesting thing is that if you use the garbage collector here before and after creating the backing file, you won't see any appreciated change in memory. And that's why this file handler is just a pointer. It's not the real file you are dealing with. The same here. Garbage collector won't report any appreciable appreciated memory change. So, and this is the way we work. Once we have the file handler VM, we can compute the number of rows that the entire matrix has, and then we can set the number of chunks. In this case, I will use chunks of 10 to the 7 rows, and this is the starting line for the file where we will compute the operations. So we'll do the operations on each chunk. Each chunk will be computed some analysis, some computation, and then when we finish with this chunk, we save the results in a partial set of variables, and then we continue to the next chunk and so on until we reach the end of the file. So this is one example on how to initialize the big matrix by chunks using some probability distributions here. Yes. And you start from the starting line and end in this variable here. And at the end of the chunk, you update the starting point and also the ending point of the chunk. So this is working with the matrix manually, but there are also some existing packages that work in combination with big memory, such as big algebra, big analytics, and also some packages that allow you to run this process of calculating things with chunks in parallel. So you can do that in many using many CPUs at the same time, and that could help you and save you time. So now let me go to the summary. We have seen several tools for monitoring the memory, like rprof and the garbage collector, and also more refined packages like pre and liveprof that give you more details. In case you want to deal with the big size files, you can use big memory. This is just one of the packages that provides you with. Other packages are, for instance, FF. Um, this is not covered here, but the idea is very similar. So something that helps me when upon working with R is that I can use tools like the Tasks Manager in Windows. In Linux, there is a tool that is called TAP or HTAP that provides you information about how the CPU and the memory is used. So, for instance, in my case, I'm using Task Manager on Windows, and I can see how the CPU usage looks like. And here, notice that I have only two cores, which means two processors that can do the things in parallel, right? So if I want to run an application in parallel mode here, I could use only two cores. And there is also one feature in the course that is called the hyper-threading. And this allows me to see that I have up to 4 cores. But in reality, the number of physical cores is 2. Just that this is using a technique called hyperthreading. And here you can also monitor the memory that you are using in your application. So I will go briefly to the solutions before uh, closing this first part of the course. So in the first exercise, the, the point was to correct these first fix me strings to get the profiling analysis using rprof. And here I did this in the solutions document. And you can see that first I get the timings if you're using RStudio and the markdown document. And you get the times. And you also see that there is a profiling analysis in detail. And you can see that several functions are being called. And if you get a detailed analysis, you see that many functions are called also during the simulations. But in the case of the second function, only the call sums is being called. So no data duplication, no data extra data allocation, and the performance, of course, is much more better in the second function. And this is a C function explicitly written for this purpose in R. In the second exercise, I asked you to do this big memory exercise. So you need first to create a file handler. And here the point was to correct some fixes in the setup, similar to what I had on the slide. So this is, as I said before, just a manual way to deal with big matrices because there are existing packages that will allow you to compute the most common statistical analysis by using the big memory package in combination. So you can see here how I computed the mean and the standard deviation, and it was done manually. So as a note, I mentioned that before, uh, the size of the matrices that I'm dealing with here are quite small, but you can use that for really big files. And in the final part, there are two uh, for loops that are doing the similar thing. Just take an array and then check whether the value of each element is less than 0.05 and assign the NA string. So you can compare the performance of these functions for different vector sizes and check the performance. And you see that the vectorized function, which is the second one, is at least in this operating system, and I'm not overloading the system with the several packages open at the same time. So the vector loop performs better, and you may think that using a vectorized operation is always good, but consider also the fact that the vectorized operation make copies of the objects that you are dealing with. So this is something that you usually don't appreciate unless you do the profiling analysis. You can check here how the profile looks like, and you will see the duplications of the data. Uh, Duplication of data is not that bad, but imagine that, as one person mentioned, you are dealing with a large array, and then you load that, and at some point, R does some duplication. We will see tomorrow why this is a problem when you are dealing with parallel computing. Because in parallel computing, you take the initial data that you provide to the master worker, and then you distribute this data to the workers that you want to work with. And if you don't pay attention to this, R will easily duplicate the data on all the workers. And if one worker is, for instance, uh, 30 megabytes and you use 10 workers, then you will exceed easily the 122 gigabytes of memory of one node in Kebnekaise, and it will give you an error. We will also see some tools to monitor the memory consumption of your code on the fly tomorrow. Is there any question? Okay, if that is not the case, yes, feel free to write on the Google Docs. I will be checking that and and share your experiences. If you have any comment, then write that, and we will check that later.